All right, it is a pleasure to be here today to talk about our new daily light integral maps. And so we'll introduce those. But before I introduce the maps, we'll kind of go back and do a little primer on what DLI actually is and how it's a useful measurement. We'll introduce the concept of DLI, and then we'll show you how to access the new DLI maps that we have an interactive website that you can go and find specific lighting information about any location in the United States. And then we'll talk about how to use that DLI information to improve your greenhouse production light management strategies. So the concept of DLI is one where we take the light intensity that's measured all day long, and we add up all the individual light measurements. And so we'll first look at how light intensity changes throughout the day. And so the unit that we like to use in the scientific community, and I think growers are becoming more familiar with, and it is micromole per square meter per second, as you can see on the y-axis. And this is an example of a perfectly sunny day outside where it's dark in the morning, sun rises, we have a peak. And in North America, we think that peak tends to be around 2,000. We know it tends to be around 2,000 micromole. And then it comes back down in the afternoon. And of course, growers are familiar with different light units. So I'll pop a few other light units up here for your reference. If you're more familiar with watts per square meter, we think of 1,000 watts per square meter as being full sunlight in the summer in North America. Foot candles, we think of the maximum that we typically get here is 10,000 foot candles. Lumens is essentially the same as foot candles. And then we can also look at lux or kilolux, and with kilolux, it's 100 kilolux is the maximum light intensity. So we can kind of reference all of these different light units, but today we'll emphasize micromole and just use that. So as I mentioned before, what we do in order to measure DLI is we simply measure the light intensity over each second of the day with a data logger. And until we add it up, we have all those individual light measurements throughout the day. And then what we're really interested in is that area that's underneath that curve. So a full sunny day in North America, you can see all that pink is the total amount of light that the plants have delivered to them. And when we think about plant growth, this is actually a much more useful and interesting concept than light intensity, because obviously light intensity is always changing. And what really is important is how much light has been delivered to the plants over the entire day. So we kind of, if you want to use the analogy of rain, we don't really care how many raindrops fell per second per square meter. What's interest is the quantity of rain that has fallen over the course of the day. So we put a rain bucket out and capture all of the raindrops. It's the same thing. We put a light sensor out and capture all of the photons of light, and that measurement is DLI, the daily light integral. Integral is to add up. Daily is obviously day, so you're adding up all the light during one day. So, and then just to show you the math, because it's really quite simple, and it can seem a little, because it's a bit of a foreign language, these units are, it can be a little bit intimidating, but simply we're taking light intensity, which is measured in micromoles per square meter per second, and we add up all of those measurements all day long, and we end up with a very big number, and then change that unit from seconds to days. So we end up getting 50,000 micromole per square meter per day. Well, that's a big number. And so what we then do is want to change the prefix on this unit from micromole to mole. And micro means 1/millionth of a mole. So the conversion is, 1 million micromoles is 1 mole. So we simply take that 50,000 micromole per square meter per day, and that is equivalent to 50 moles per square meter per day. And we often, in the greenhouse vernacular, we will write it like this. Instead of the kind of the fancy mathematic units, we'll just simply say 50 moles per day. And that refers to the total light delivered to your crop during a given day. So of course the DLI changes throughout the year, and it changes day to day. On the left you see an example where it's 50 moles per day, a perfectly sunny day in the summer. On the right is maybe a typical winter day, and especially the northern latitudes, you get a cloudy day. The sun's kind of constantly changing throughout the day, but that area under the curve is obviously much less, and that adds up to 4 moles per day on that particular example. So obviously that's a pretty low light day. And you can see how DLI kind of communicates that quite nicely. So that's the background on DLI. The next step is, well, how to get your own DLI information to know what light levels you have in your part of the country. So we have created these maps, and if you simply click here on the American Flora Endowment website, you can go into the website and do a search on DLI maps, and this page will pop up. And if you click on this link, a website will open up. And this is an interactive website. It's a very slow, unfortunately, there's a lot of data being processed in order to, for you to access this information. So it can be a little frustrating if you click 3 times in a row, like you go click, 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 and expect it to go zoom, zoom, zoom as you try to get into your specific location. That will not work well. You kind of click, you wait for the screen to adjust, and then you click again and until you zoom in and to exactly where you want. And I'll show you that. So, but when you first go into the site, you'll see this is the annual DLI for Alaska, Hawaii, and other 48 states. And you can click on any of these months and get the monthly DLI. There's a legend over here to translate the colors into a range if you want to do that. In this example, we'll click and we clicked on January up here, and you see all the colors change, and you see the patterns of DLI delivered to the different parts of the country. And you can see why it can be difficult to grow plants in Alaska in January, because there is very, very low light. We'll click on this again and we'll zoom in, and now you see the entire country. You see this very interesting pattern across the country, and pretty dramatic differences in light levels from the Southwest and South Florida compared to the Canadian border and the Pacific Northwest. We'll click in on St. Louis for this example. And so we've clicked in, and you can see Missouri, and you can see all the pixels, and each pixel there represents a 100 square kilometer area. And each pixel has a unique set of data that you can click on. And you should not interpret the color graphs are simply to give you, show you the trends, but all the data in the blue is not all the same. It just happens to be, in the range of 15 to 20 moles per day. The purple is in the range of 10 to 15 moles per day. But where you have that interface of purple and blue, that doesn't mean there's any more dramatic change there than any other pixels. That just happens to be where we draw the line between the 10 to 15 mole per day range and the 15 to 20 mole per day range. So we'll click in a little closer on this one specific pixel that's near St. Louis, and what pops up is the annual DLI value as well as the monthly DLI values. And you can drag on the little bar here, and you'll see the lower part of that window has October through December, and it actually shows you a little graph to show you the trends through the year, from the low DLI values in the winter to the higher values in the summer. And so just to zoom in on that one more time, you can see all 12 months there and the values. So that's kind of cool and interesting. What do you do with that is the next step. And for this example, I just took those 12 data points and plotted them on a little curve just to demonstrate how DLI changes quite dramatically during the year. And we all know this intuitively because we know our plants grow a lot better in the summer than in the winter. But it's pretty remarkable to see, and this is St. Louis, the outdoor DLI, the low point of the year is December, and that's the average day in December is 13 moles per day. And then you get into January and it's also low, but then from February we jump to 22, and then March we're at 29, April 37. So basically over 3 months we've almost tripled the total amount of light available for plant growth. And obviously the plants respond to this with much faster and better growth. So, but the one caveat with the maps as they stand, that is all outdoor weather data. And most of us are probably interested in what the indoor weather data is, or what indoor light environment. And so we have to compensate, take the maps and compensate, and we are compensating for greenhouse light transmission. So if we look at how much light is outside versus inside, it can be dramatically different because light is scattered by the glazing material. It's intercepted by the infrastructure, the support beams and such, and the trusses. And so the amount of light that actually gets to your crop inside of a greenhouse is typically 35 to 65% of the light that is actually outdoors. If you just pick one number to guess what is inside versus outside, I would pick the number 50%. That's a reasonable expectation of how much of the light actually gets in. So that's not a very good percentage, but that is what it is. And those percentages actually vary seasonally. So the daily light transmission in the winter is worse than it is in the summer because the sun's at a lower angle in the sky. The light from the sun tends to reflect off of the greenhouse more than when the sun is directly overhead or close to being directly overhead in the summer months, and the light comes down more perpendicular to the greenhouse structure, and you get better penetration to the greenhouse benches and floors. So in the winter, we're looking at 35 to 45% transmissions, spring, fall, about 50%, and the summer up to 65, potentially even 70%. So if we go back to taking our DLI numbers off of our maps, we have, again, the outside data, and if we assume 35 to 45% transmission in the winter and higher transmission in the summer, then the blue line represents the inside DLI. And so what you see, even though we can get 50 moles per day outside, we may only be at 30 inside in the summer, and in the winter we're down to 4 and 5 and under 10. And of course, those numbers, if you aren't familiar with them, may not be meaningful. And so we'll go over some guidelines as to what levels are really important for plant growth, and we'll talk about that in a second. The other thing is that one needs to consider is in the summer, we tend to put shade cloth on greenhouses, not because the plants don't like a lot of light, it's because we have to have temperature control. Without shade cloth, the greenhouses get too hot. And so rarely do you actually ever measure 30 moles per day in a greenhouse. The highest we usually ever measure is about 20. And actually one problem that often happens in commercial facilities is that the light level is getting brighter in January, February, March, and then sometime in that spring period, depending on where we're located, we end up putting some shade on that greenhouse. And when we put 50% or 60% shade on the greenhouse, we can reduce the DLI dramatically. And so now, even though it is summer, we may be at 10 moles per day, under 15, and in some cases, lower than that. We see that in propagation, where sometimes growers just get a little too exuberant about their shade cloth, and they make a very comfortable environment in the greenhouse, but the light is actually much lower than you may anticipate, because our eyes are not very good sensors. You really cannot rely on your eye to estimate DLI. You really have to have a sensor to get a good measurement. So anyway, the take-home message is the light levels in the summer can be often, I shouldn't say often, but they can be as low as winter light levels if we're not careful with the shade cloth that we put on. How much light do plants need? It varies depending on the crop you're growing and the stage of development. But in general, these are the three main categories that I think make sense. In propagation, we want to have at a minimum 4 to 5 moles per day and up to 10. If we have over 10, we start to have some stress-related problems. Plants don't take up water very well without roots, or if the root system's not well developed on an unrooted, on a cutting that's just initiated roots. You know, over 10 moles per day tends to be a bit stressful. You're gonna have wilting. So 4 to 10 is our target in propagation. On most of our flowering crops in greenhouses, I would shoot for a minimum of 10 and then a maximum of 20. Again, there's not a lot of benefit on ornamentals going over 20. You can get a very nice crop with 10 or higher. When you're starting below 10, you do sacrifice quality. You know, it's not that the plant is unsellable if you have 8 moles per day, but it's not as good as I think we are normally expecting. So 10 to 20 are our expectations for flowering crops. Now, if you're growing vegetable crops, some crop that you're harvesting, cut flowers would be the same thing. Then really we want to be at 20 and higher. Now we can be challenged with heat if we start getting up too high, but we want to be fairly high, and that tends to be much more important on crops that we're harvesting some part of the crop compared to flowering crops where we're just trying to have a nice ornamental plant. If we go back, now that we see these guidelines, you can see, you know, you take a day in January, the average in St. Louis is 6 moles per day. Well, you can imagine there are a number of days that are much lower than that, and a number, you know, some days that are higher. But so the typical range in St. Louis is going to be, you know, lows of 1 or 2 moles per day and highs of 10 or 15. So, or maybe even 15 is probably even exaggerating. So we're below really our goal. And so it is at these times a year, January, February, and then on the other end of the year, November, December, that supplemental lighting is obviously beneficial because we're bringing those low DLIs up to the minimums that like 10 moles per day to produce a good crop. Now, how much light do we actually get from supplemental lighting? And this is often a bit of a surprise. You know, when you look at the sun is delivering 50 moles per day outside in the summer, and you think, well, supplemental lighting has got to be close to sunlight. But this chart will show you that the amount of light that we really get from artificial lights is really not all that impressive. Here we have 3 different light intensities and 50, 7500 micromole. Those are the typical range that you would design a supplemental lighting system in a commercial greenhouse, and probably 50 is the most common. How much the light intensity that high pressure sodium lamps, for example, would deliver. If we have those lamps turn on for 4 hours, we don't even get 1 mole per day. If we have 8 hours, we have 1.4, 12 hours, 2.2, and 16 hours of light from high pressure sodium lamps delivering 50 micromoles per day will give us basically 3 moles per day. So that is not anywhere near what sunlight can give us. But if, you know, I'm sitting in here on a cloudy day in Iowa and we may only be getting, you know, 3 moles per day out in our greenhouse, if I can add 3 moles with supplemental lighting, that's 100% improvement going from 3 to 6. So that's significant. Now, if I'm here on a sunny day, like we had here yesterday, we probably had 10 to 12 moles per day delivered in the greenhouse. There's no reason to turn on the lamps on a day that we already are getting 10 moles per day. You would get a benefit in plant growth, but is it economical at that point to be turning on the lamps? And Mark Van Ersch will be talking more about that in the second half of this webinar. And one of my last points here will be there are growers now are interested in vertical farming, indoor farming type situations. And in those situations, we have a constant light intensity throughout the day. And just to relate DLI to those types of situations. In this example, we have the pink line that's showing outdoor or greenhouse light intensity maxing out at 1,000 micromole in the middle of the day. That pink line, if you look at the area under that curve, we would get 22 moles per day. If we are trying to simulate a day with 22 moles per day in a sole source lighting situation where there's no sunlight, only artificial lights, and we have the lights on for 12 hours, we have to deliver a light intensity of 525 micromole. So that is the blue line here. That means we turn the lamps on at 7, we deliver 525 all day long, we turn them off at 7 p.m. 12 hours with 525 micromole. That area under that curve is also 22 moles per day. If we go to an 18-hour photo period, so we're turning on at 4 a.m. and going out to, would this be 10 p.m., we would have to deliver 350 micromole during that time frame so that the area under that green line would equal to 22 moles per day. So it's different ways of delivering the same amount of light, in other words. So finally, we have these maps, the interactive site that I showed you. We also have some posters that the American Floral Endowment has printed that you can request from them to send you a poster, and I believe they will. And it's kind of a neat little way of seeing. You can see in the winter months how the colors are these blues and purples and pinks. And then as you transition in the spring from February to March to April, you can see that the light levels change dramatically from month to month. And then, May, June, July are all, fairly similar. And then in the fall, you again see this rapid transition from August to September to October where the light levels change quite dramatically. And when you have all the maps here together, you actually see one other thing that I think is quite interesting. In the winter months, you can see the patterns of DLI across North America are in a horizontal pattern where it's dark across the north and it's brighter as you go south. As you go to summer, those horizontal patterns really disappear, and the differences tend to be more east-west. I mean, for example, Florida is the same color yellow as the Northeast in June, whereas in December, there's quite a bit of difference where Florida is in near 25 moles per day, South Florida, and northern Maine is 5 to 10. So that's a huge difference. And so what happens is in the winter months, the light intensity is brighter in the south and the day length is longer in the south. So you get longer days, brighter light intensity. The south is just benefits. It's much higher DLI. In the summer, the day lengths are actually longer in the north than in the south. It's still brighter intensities in the southern states, but because you have longer days in the north, it tends to balance out, and so you don't see the north-south differences that you see in the winter months. You see east-west differences because that tends to be rainfall related. The number of sunny days that you have in the southwest is so much higher than in the east that the differences are mostly east-west, not north-south. All right, so I guess I can open it up for questions.